If a spillway is too small, a dam can collapse, affecting life and the overall environment. At the same time, if it is too large, millions of dollars are wasted. So there is a need to strike a balance between safety and cost. In this video, I'll show you how engineers determine the correct size of a dam spillway step by step. Hello, I'm Ponciano. I've been designing hydraulic structures for the past 9 years. These are the same engineering methods used when designing real dams around the world. And if you want to learn more practical engineering workflows, make sure you subscribe to the channel to get more practical insights. But before we size a spillway, we must first understand what problem that the spillway is solving. A spillway is a safety valve of a dam. Its simple job is to allow all the excess water to leave the reservoir safely. Because without a spillway, water will just rise until it flows over the dam crest, a scenario commonly called overtopping, and it's extremely dangerous for most dams. And because of this, the spillway must be able to safely pass the extreme floods. These extreme floods are often determined through hydrology. So how do we determine the extreme floods? We make sure we determine the design flood. So the first step in spillway design is estimating the design flood that the dam must safely pass. So the design flood for many dams, engineers use the probable maximum flood, often abbreviated as PMF. The PMF represents the largest flood that could physically occur in a watershed. So it is derived from probable maximum precipitation, and probable maximum precipitation is the greatest depth of rainfall that is physically possible over a catchment. We should know that it is not based on probability like 100-year or 1000-year storms. Instead, it is based on atmospheric physics, moisture limits, and storm maximization. There are some few methods that are commonly used to determine the PMP. One of the most widely used methods is a moisture maximization. This is normally used by World Meteorological Organization and National Oceanic and Atmospheric Administration. But the basic idea behind this is we take the largest recorded storm and increase moisture to maximum possible, and through that we can obtain the meteorological PMP. Another common method is also called storm transposition, whereby we move a severe storm to your catchment. For instance, if storm occurs in mountainous areas, we apply our basins. Then we adjust the elevation, temperature, and the moisture to match the site condition. Engineers sometimes also use envelope curves, whereby the maximum rainfall in various areas near the catchments are plotted and the upper envelope is taken. It is a very common method that is adopted during preliminary studies. So we plot rainfall data for various areas, then we draw the upper boundary. That upper boundary becomes the PMP. Or make a graph and generate an equation which you can then adopt to determine the PMP depending on the size of the catchment. So the design flood is chosen based on the size of the dam. If it's a small dam like 50 to 100-year flood, or a medium dam like 100 to 500-year flood, we normally do flood frequency analysis to come out with the design flood. But for larger dams, we normally make use of probable maximum precipitation, which is derived from PMP. So to come with the PMF, we first have to estimate the PMP using one of the methods that we just discussed, and then from there we make sure we convert the PMP into design storm. Once that is done, we convert the rainfall into excess rainfall, because not all the rainfall that falls into the catchment is taken out as runoff. We can apply various methods like use of SCN method, which helps us to come with the excess rainfall the catchment is going to undergo through. And through that, we are able to generate the PMF hydrograph. Now, this hydrograph finally helps us to come with a peak discharge of the inflow. So once we have the PMF hydrograph plotted, we now make sure that we do reservoir routing. So once the flat hydrograph is known, engineers perform reservoir routing. And reservoir routing normally calculates how the flood behaves inside the reservoir. because not all flat water passes immediately through that spillway. Some of them are kept in the dam, in the reservoir for some time, and then discharged later on. So this storage normally reduces the peak outflow. One of the most commonly used methods is the modified pulse method, which helps to come out with the reservoir routing analysis. Reservoir routing therefore helps to determine the maximum reservoir level, peak spillway discharge, and the timing of the peak flood. So the key result engineers obtain is the maximum outflow that the spillway must pass. Then next we make sure that we select the spillway type. So before calculating the size, engineers select the type of spillway. The common spillway types include auger spillway, side channel spillway, shaft spillway, siphon spillway, and labyrinth spillway. And the selection normally depends on the dam height, the foundation conditions, the site topography, or the required discharge capacity. But many dams use auger spillway because it efficiently passes large floods. So once we have chosen the type of the spillway, the next step is to choose the right spillway discharge equation. After determining the design discharge, engineers use hydraulic equations now to size the spillway. For instance, for an auger spillway, the discharge equation is Q equals to CLH power 3 over 2, where Q is the discharge in Qmax, and L is the spillway crest length, H is the height over the spillway crest. It is the difference between the full reservoir level and the maximum water line, which that difference gives us the H. And then C, which is the discharge coefficient. C is the discharge coefficient, which is dependent on the phase of the auger crest. So let's take an example. Assume that we have a design flood. From our reservoir routing, we got an outflow discharge of 2000 cubic per second, and our height over spillway crest is 5 meters, and the spillway is having a coefficient of 2.2. Now using the auger spillway equation, we can estimate the length of the spillway, which becomes 82 meters. Now this calculation determines the required crest length of the spillway, which is able to pass out the flood safely. If you're getting some value from this, please like the video. The next step is to check for energy dissipation. Because water leaving the spillway moves extremely fast, if not controlled, it can erode the riverbed downstream. Engineers therefore design energy dissipation structures. The common ones include the stealing basin, flip buckets, and the plunge pools. The major motive of this is to slow down the energy, transform the energy from supercritical to subcritical flow, so that there is no scoring and erosion on the downstream side of the dam. Once that is done, we ensure safety checks for our designs. So engineers perform several safety checks. We clarify the dam crest elevation. We check for the maximum water level if it's well computed, and also check for the freeboard. The freeboard is dependent on the fetch and the wind speed in the project area. We also do safety checks on the spillway capacity during extreme floods. We also do structural stability analysis on the structure. If the spillway cannot safely pass the design flood, engineers increase its width or capacity. So the key takeaway from this is sizing a dam spillway is not a guesswork. It requires a combination of hydrology, hydraulic engineering, reservoir analysis, safety evaluation, and cost consideration. A properly designed spillway ensures that the largest floods can pass without damaging the dam. If you want to learn more practical engineering workflows, make sure you subscribe